In this video, I'll be helping you with the ALEKS problem type called using the rational zeros theorem to find all zeros of a polynomial, complex zeros. And in this example, we're given g of x, and we're asked to find all zeros for this function. We know that we're using the rational zeros theorem, but we also know that we should end up with some complex zeros. So we'll start with the rational zeros theorem and see where that leads us. And for this example, using the rational zeros theorem, we'll start by identifying our p's and our q's, p being the factors of that last term in the polynomial, the constant term, here 5. Our factors of 5 for p will be plus or minus 5 and plus or minus 1. And then for q, we'll do the same thing, but looking at the leading coefficient, here 7. Our possible factors are plus or minus 7 and plus or minus 1. So with these p's and q's, our potential zeros will come from all of the possible p's over q's. So I'll start off assuming that q is the plus or minus 1. That would give us 5 over 1. So plus or minus 5 over 1 is just 5. Or this one over the q1 would give me plus or minus 1. And then the other possibility is that the q is plus or minus 7. And if the p were still the 5, that would be plus or minus 5/7. And then lastly, the p could be the factors of 1, again over the 7, would give us plus or minus 1/7. So we have listed out all of our possible rational zeros. And now to find the zeros, we can just use synthetic division to see if any of these work. Setting up this polynomial for synthetic division, we would use each of the leading coefficients and their signs and make sure that we don't have any missing terms. So we've got a 4th degree, we would have to have a 3rd degree. If necessary, we could use zeros as placeholders, but here nothing's missing. We have a 7, x4, a 40, x3, a 24, x squared, a minus 4, x, and a plus 5 constant. So from here, we can start trying out our potential zeros that we have listed. We might as well start with the easiest ones first. I'll start off trying a positive 1, so that if I bring down that 7, 1 times 7 is 7, plus 40 is 47, and then 1 times 47 is 47. Adding again here, this is 71. 1 times 71 is 71. And I can sort of see now that this isn't going to work out, because adding here would be 67. 1 times 67 is 67. We are not getting a 0, so the 1 is not dividing in evenly. So we've eliminated positive 1. We should try again with negative 1. Again, bringing down the 7. Negative 1 times 7 is negative 7. Adding negative 7 and 40 is a positive 33. Negative 1 times 33 is negative 33. Adding here again gives us a negative 9. Negative 1 times negative 9 is a positive 9, which adding to negative 4 gives us a 5. And this is going to work for us. Negative 1 times 5 is negative 5. So we have our 0 remainder. We found our first 0 is negative 1. And from here we can continue, and we can actually work with a smaller synthetic division, because each of these can now be my coefficients. So I can set up synthetic division with 7, 33, negative 9, and 5. And I'm going to keep trying our potential zeros labeled here as P and Q. I'll move on to our 5s. I'll first try a positive 5. Bringing down the 7, 5 times 7 is 35. Adding here gives me a 68. And I'm already suspicious that this is not going to give me 0, because that 68 times 5 would be 340. Adding to the negative 9, 331. I can already tell that this is not going to give me a 0 remainder. So I can eliminate a positive 5, but we do need to try a negative 5 as well. Bringing down that 7, negative 5 times 7, a negative 35. Adding the 33 gives me a negative 2. Negative 5 times negative 2 is a positive 10. Adding here again is 1. Negative 5 times 1 is a negative 5. This again gives me a 0. So I have found my second 0, negative 5. And from here, I'm down to just 3 terms in our quadratic. And since I'm expecting complex zeros, if I write this back into its quadratic form, that would be 7x squared minus 2x plus 1. From here, since I'm expecting some complex zeros, I can get at those by using the quadratic formula. So moving up here, the quadratic formula says negative b plus or minus the square root of b squared minus 4ac all over 2a. Here, our a is 7, our b is negative 2, and our c is 1. So plugging into the quadratic formula, negative b is negative 2, that would be a positive 2 plus or minus the square root. B squared, b is again negative 2. Negative 2 squared is 4. Minus 4 times a, which is 7, times c, which is 1, all over. In the denominator, we have 2 times a, so 2 times 7 would give us 14 in that denominator. And then we can start to simplify. Under the radical, this would be 4 minus 4 times 7 times 1 is 28. 4 minus 28, with that 14 in the denominator. And from here, we can continue to simplify. Under the radical, we now have 4 minus 28, or a negative 24. That negative underneath the radical is going to give us our complex root. But from here, we can simplify a bit more. This negative can come outside of the radical as an I, and the 24 can be broken down into a 6 times 4, and the 4 would come out as a 2 since it's a perfect square. So just to show that, the negative comes out as an I, the 24 is 4 times 6, and then since the square root of 4 is 2, this would be 2i, square root of 6. And since this denominator is 14, and we can separate the numerator into each part being over 14, this will continue to simplify to just 1 over 7 plus or minus. The 2 goes into 14 7 times. So this would be just I square roots of 6 over 7. These are our last 2 zeros. They're both complex. The first one is 1/7 plus I square roots of 6 over 7. The second one is the negative, so 1/7 minus I square roots of 6 over 7. And we can recall that earlier we found -1 and -5 as zeros. So we'll list those as well. -1 and -5. We have 4 total zeros, 2 complex and 2 real. I hope you found this video helpful. You can find a complete list of Timely Math Tutor videos organized by course and curriculum at timelymathtutor.com.